Okay, so come back to another your problem. Then we will see that your what you call that RL circuit and this right now. So in figure I will come to that. In figure 51, the switch has been closed right for a long time and is open at t is equal to 0. So we have to determine I and V for all time, right. So it is given that switch has been closed for a long time, and that means this switch was closed for a long time, and your I mean it was closed for a this switch was closed for a long time, and at t is equal to 0 this switch is opened, right. Now question is this your this 100-volt source is there, but one step input is also there here, that is 15 ut volt, right. So in general your when you write 15 of ut, that is equal to your this one is equal to 0 when t less than 0 and is equal to 15 when t greater than 0, right. So in that case, that means in general your ut actually is equal to 0 for t less than 0 and it is 1 for t greater than 0, right. So that is why this 15 ut your what is equal to 0 for t less than 0, that is your what you call the past history. That means let me clear it. So that means the switch was closed for a long time. So in this case what will happen, that is your for t less than 0. So in that case what will happen, that 15 ut, right. So is equal to, I told you it is 0 for t less than 0 and it is 15 for t greater than 0. That means in that case what will happen, this is your what you call this was closed for a long time, and that means this 15 ut voltage source actually this is becoming 0. That means it will be like this, right. So just join it, because this thing is actually is equal to 0 because switch was closed for a long time, right. So as switch was closed for a long time, that means to this and this 100-volt DC source is there, this is closed, that means this capacitor will act as an open circuit, right. So from the if it acts as an open circuit, that means that a switch was closed for a long time, that means your Vc, that is Vc is equal to say V, right, is equal to 0 minus is equal to this 100 volt, right. So this is your what you call, this is your Vc 0 minus, and at the same time you can easily, and as this 10 ohm and 20 ohm are in your what you call are in parallel, right, because this voltage is 0. So it is short, just for the purpose of explanation. So and your what you call easily you can compute I, because this will act as an open circuit. So equivalent circuit is shown, I have drawn it here, right. So in this case everything is written there, whatever I said everything is explained here, right, it is 15. So in this case what will happen, the circuit will be like this. So this is capacitor was there, it will act as an open circuit, and this is I, and this is 10 ohm and 20 ohm are in parallel, and this is 100 volt, right. So V 0 plus your V is equal to 100 volt and I will be equal to minus V by 10, that is minus 10 ampere. Actually if you just 1 minute, if you try to find out this I, the direction is taken in this way, So if we say that just for your this thing, this voltage and this plus minus voltage means this is the voltage V, right. So this is plus, this is minus. So it is basically what will happen, 10 I, if we move like this, 10 I plus V is equal to 0. So I is equal to minus V by 10, that is equal to minus 100 by 10, that is equal to minus 10 ampere, right. So let me clear it. So in this case, that is why it is given I is equal to minus V by 10, it is minus 10 ampere, and the capacitor voltage, if you look into the circuit, when switch is open at t is equal to 0, the capacitor voltage, that means as soon as it is open this voltage source should not be there, because it is disconnected, and that is at t is equal to 0 it is open. So for t greater than 0 this 15 volt step input will be here, and at the and capacitor voltage cannot change instantaneously. So in that case what will happen, V 0 minus is equal to V 0 plus, that will be your 100 volt. So, now in this case 15 volt source is there and this is 10 I and this is your V 1 upon 4 farad. Now, after a long time, I mean if you look into that since the capacitor voltage cannot change instantaneously. So, V 0 is equal to V 0 minus, that is 100 volt. Now, for t greater than 0, the switch is open and the 10 volt source is disconnected from the circuit, that I told you. Then this 15 UT volt source is now operative and the circuit it is like this. Now, at steady state, if you look into the steady state, that means what will be your V infinity. Suppose at steady state this capacitor will act as open circuit, that means circuit will be something like this, right. This is your 15 volt, this is 10 ohm, this is your 20 ohm and this capacitor is acting as open circuit at steady state to the DC. So, in that case what will happen, this VSS is equal to actually V infinity is equal to is V, this is your V at steady state. Now, as you can easily, as this is open circuit, so this is your 10 ohm and this is your 20 ohm. So, you can easily find out what is the current I through this circuit. This I is given, it is open circuit. So, I is actually is equal to 15 divided by 20 plus 10, that is 30. So, is equal to half ampere, that is your I, right. Then what is V infinity then? V infinity will be, that is a steady state value, this is open circuit, this I current is flowing, this I is half and it is 20. So, that is equal to your 10 volt, right. So, V infinity is the 10 volt, right. So, this circuit is done for you. So, in this case your this is V infinity is equal to 10 volt. Now, when you will find out your R Thevenin, so R Thevenin means your for getting the Thevenin, I showed you the circuit. This is looking from this point you have to find out, at that time you have to short this one. So, 10 ohm and 20 ohm are in parallel, right. So, you have to short this. So, in this case your R Thevenin will be 10 into 20 by 10 plus 20, right. So, it will be 200 divided by 30 is equal to 20 by 3 ohm, right. That is R Thevenin. Therefore, time constant tau will be is equal to C into R Thevenin. So, C is given your 1 upon 4 farad. So, it is 1 upon 4 into 20 by 3. So, that is equal to 5 by 3 second. This is the tau, right. So, let me clear it. All these calculations are there, but I am making it such that so in this case your this is tau, that is 5 by 3 second, and R Thevenin we got 20 by 3. Now, we know this formula that V t is equal to V infinity plus V 0 minus V infinity e to the power minus t upon tau. So, V infinity we got 10, V 0 is equal to 100 and V infinity 10. So, 100 minus 10 into tau is equal to your 5 by 3. So, it will be e to the power minus 3 t by 5. So, V t will be 10 plus 10 into e to the power minus 3 t by 5 volt, right. Now, from figure 53 I is equal to, now if you come to figure your 53, that I is equal to. So, one thing is there, that this voltage V means no other element is there. So, same voltage will impress across your 20 ohm resistance. So, this current, say it is I 1 and through this capacitor, say it is your I c, then I 1 will be say V by 20, this is I 1, and I c will be this C, this is your C, the capacitor, C into dV by dt, right. That means, I is equal to your V by 20 plus C into dV by dt, right. So, let me clear it. So, if you from that only we are writing this equation, that I is equal to V by 20 plus C into dV by dt. So, that means your what you call that you put that expression of V, right. So, every time I am not writing that your V t and V t, if you want you can put it, this is V t, but it is understandable, right. So, put the expression of V t here, this expression you put it here, right, and take the derivative of this one. So, this is the second term, that C is equal to 1 upon 4 farad into dV by dt, right. So, let me clear this. So, in this case your I is equal to after your making simplification, half plus 9 by 2 e to the power minus 3 t by 5 minus 27 upon 2 e to the power minus 3 t by 5. That means I is equal to half minus 9 e to the power minus 3 t by 5 ampere, right. Note that this V plus 10 I is equal to 15 is satisfied. If you go to this circuit, right, your go to this circuit, I mean if you suppose I want to apply KVL, right, I want to apply KVL. So, this voltage V means, suppose if I make it like this voltage V means it is 10 I plus V minus 15 is equal to 0. That means 10 I plus V is equal to 15. You check it, it will be satisfied, right. So, let me clear it. Sorry. So, that is why it is written this is actually satisfied. Therefore, for all t V is equal to 100 volt, that is your V 0 minus is equal to 100 volt for t less than 0, and 10 plus 90 to the power minus 3 t by 5 volt for t greater than 0. And similarly, for I, for t less than 0 it is minus 10 ampere we have computed, and for t greater than 0 it is half minus 9 e to the power minus 3 t by 5 ampere, that is t greater than 0, right. So, another way, now this is, I hope you have understood this, things are not at all difficult one, right. So, another way of looking at the complete response is to break into two components. One is natural response and other force response. I mean the response has two things, you can break it, one is natural response and other is the force response, right. So, we can also cite the total complete response. So, complete response is equal to natural response, that is stored energy, that is your source free circuit, that is the natural response we got, plus force response, that is independent source, maybe voltage source or current source, independent source, right. So, that means, let me clear it. That means V is equal to natural response V n plus force response V f. This is the equation 59, right. Therefore, equation from equation 48 it can be rewritten as, I am writing here equation 48. From equation 48 we are writing this, actually equation 40 somewhere I am writing, say here Vt is equal to, this equation was equation 48 Vs plus your Vs, then your V0, you take V0 common, right, then 1 your 1 minus e to the power minus t upon tau, right. I mean just this equation you can write that V0 it is 1 your what you call, it is V0 then into your just 1 minute e to the V0 e to the power minus t by tau, then plus Vs, then V0 will be your just 1 minute, let me make it here, this is V0 e to the power minus t by tau plus Vs minus Vs e to the power minus t by tau, right. So, that is actually is equal to your Vs plus V0 minus Vs e to the power minus t by tau. So, it is V0 minus your, sorry, let me clear it. So, it is actually your Vs, right, plus V0 minus Vs e to the power minus t by tau, that is your equation 48, right. So, this is actually V infinity plus V0 minus V infinity e to the power minus t by tau. So, if you that V0 e to the power minus t by tau you write it here, and there Vs minus Vs e to the power minus t by tau, you take Vs common. So, it will be 1 minus e to the power minus t by tau, right. So, that means that Vn, let me clear it, that means the Vn, that is your first term, is V0 e to the power minus t by tau, that is natural response. For source free circuit we have seen that, right, for source free circuit we have seen that, and this is actually we call force response, that is that is due to that external force, that is your nothing but that your voltage source, right. So, this is actually Vn and this is your Vf. So, Vn is equal to V0 e to the power minus t by tau, the natural response, and Vf is equal to Vs 1 minus e to the power minus t by tau, that is your force response, right. So, let me clear it. So, this way this equation, your equation 48 can be written in this way. So, this is equation 59, 60, 61 and 62. Therefore, natural response V n is already expressed in section 6.2 that we have done it. So, V f is known as the force response because it is produced by the circuit when the external force is applied, that is, in this case it is a voltage source, right. Now, the current response of parallel RC circuit. So, now consider that your this circuit, that is your parallel RC circuit, but a current source is there. So, in this case also it is IUT is given, and you know that you know that ut is equal to, it is 0 for t less than 0, it is 1 for t greater than 1, right. Therefore, my IUT is equal to 0 for t less than 0 and it is I for t greater than 0. So, a step input, right, and is a parallel RC circuit. So, let me clear it. So, if it suppose when your what you call that when for t greater than 0, right. So, IUT will be equal to I, because ut is equal to 1, right. So, in this case if ut is not there for t greater than 0, say, then it represent by say for your understanding it is I, right. And if your what you call, if the circuit has reached steady state, then this will act as an open circuit. This will act as open circuit. That means the voltage across this capacitor V c, that is we call it, or what you call, that is your steady state response, or your that is V c infinity, right. So, in that case V c will be V steady state is equal to same thing V c infinity, and this I current will be flowing like this. So, it will be equal to I into R, right. I hope this is understandable to you. So, in this case, based on that, and tau is equal to your time constant, that C into R, right. So, using this natural response and force response, we will try to obtain the your what you call expression of the your voltage or current, whatever you want. So, let me clear it. So, in this case your, so initially, that is why I told you that V c your, and initially we assume that initial voltage of the capacitor was V c 0 is equal to V 0, that we are assuming it may be 0 also, but we are assuming that V c 0 is equal to V 0, right. And at steady state I told you V c infinity is equal to I R. So, we know this from equation 648 that V c 2 V c t is equal to V c infinity plus V c 0 minus V c infinity to the power minus t by tau, right. Therefore, V c t is equal to I R, V c infinity we have got I R plus V 0, because initial value of capacitor we assume it is charged at V 0. So, V 0, V c infinity is I R. So, V 0 minus I R e to the power minus t by tau, or we can write V 0 e to the power minus t by tau, I mean this V 0 into multiplied by e to the power minus t by tau, then plus I R minus I R e to the power minus t by tau. So, take I R common, 1 minus e to the power minus t by tau. This is equation 63. So, V n is natural response, that is V 0 e to the power minus t by tau, like a source free circuit, and V f is equal to force response, that is I R into 1 minus e to the power minus t by tau, right. So, after this, so this is a simple parallel RC circuit with a current source, right, your step input, right. So, now next is the step response of an RL circuit. So, this is the circuit, this next we will go for step response of an RL circuit. So, in this case, that figure 55 shows RL circuit and may be replaced by the circuit shown in figure 56. So, this is your RL circuit. Suppose that t is equal to 0, the switch is closed, right. So, this is your what you call a simple, the way we consider RC circuit, here also it is simply RL circuit. This is L, and a voltage across L, that is inductor, is V t, right, and polarity is marked Li, sorry, plus minus, and this current I is flowing. Now, your in general when the switch before moving further, when the switch is closed, it will be like this, and at steady state this inductors act as a short circuit, right. At steady state inductors act as a short circuit, and if this is the current I, that means at steady state I infinity will be V s upon R, right. That is of course t greater than 0. After switching, switch is closed, right. Inductor act as your what you call that as your short circuit, capacitor acts as open circuit to steady state of DC. So, let me clear it. So, this circuit it can be redrawn like this, that is, it will be V step input Vs ut and R, and this is L same as before Vt at same thing, it is same thing, that Vs ut, right, is equal to your 0 for t less than 0 and it is equal to Vs for t greater than 0, right. So, that is why this is written as Vs ut. So, let me clear it. So, our objective is to find the inductor current I, this is the inductor current I, right. As the circuit response, we will use the technique, that equation 59 to 62, that is this equation to 59 to 62, that means this your what you call this this equation, these equations, that for 59, 60, 61 and 62, using this V is equal to V n plus V f. Similarly, we will apply for I is equal to I n plus I f, same concept. So, in this case what we will do, that we will write I is equal to I n plus I f. I n is the natural response of the current and I f is the force response of the current. So, natural response is always a decaying your what you call exponential, right. So, that we have seen that it is all. So, we can write I n is equal to say A into e to the power minus t upon tau, right, and it is LR circuit or say simply RL circuit. So, tau is equal to L by R, the time constant. So, this is equation 67 and A is a constant which you have to determine, and we know that natural response is always a decay or what we call decaying exponential. So, directly we write I n is equal to A into e to the power minus t by tau, right. So, A can be determined later, we will see that. Now, force response is the value of the current after a long time after the switch figure is closed, right. So, we always know that after 5 time constant, that is 5 tau, the natural response essentially dies out. So, at that time t greater than equal to say 5 tau, the inductor becomes a short circuit and the voltage across it is 0, right. So, that means I told you initially for this circuit, when switch is your what you call for this circuit, when switch is closed and place it for a long time, so inductors act as a short circuit. So, naturally your what you call, you can that your I infinity is equal to Vs upon R, right. So, this is your I f, that is the force response, this is nothing but I infinity is equal to your what you call Vs upon R, right. So, if it is so, then equation 67 and 68 it can be written as I is equal to, it is natural response, A is equal A into e to the power minus t by tau, and this is your force response Vs upon R, that is the steady state one, that is the I f is equal to nothing but I infinity, right. So, I f, the force response is nothing but I steady state, that is I infinity, that is Vs upon R, right. So, that, and we assume, let me clear it, we assume that I0 be the initial current through the inductor, right. We will assume that, which may come from a source other than Vs. So, we know that current through inductor cannot change instantaneously, that means at the time of switch, at the time switch is closed, I0 plus is equal to I0 minus is equal to I0, because current through inductor cannot change instantaneously. Therefore, at t is equal to 0, I is equal to I0. So, in equation 69 becomes, that means here your what you call here at t is equal to 0, you put I is equal to capital I suffix 0, right. So, if you do so, that I0 is equal to, then you will get capital I0, you will get A plus Vs upon R, from which you will get A is equal to I0 minus Vs upon R. This A value, input it in equation 69, then you will get It is equal to I0 minus Vs upon R e to the power minus t by tau plus Vs upon R, this is equation 72. Therefore, It is equal to, this term writing first, Vs upon R plus I0 minus Vs upon R e to the power minus t upon tau, right. So, this equation is nothing but look into that, this is I infinity, Vs upon R is I infinity here, right, and this I0 is the initial value, that is your I0, again it is I0 minus I infinity e to the power minus t upon tau, same as before, right, where I0 is equal to capital I suffix 0 and I told you I infinity is equal to Vs upon R, right. So, note that if the switching takes place at time t is equal to t 0, if it is at t, if switching takes place at t is equal to t 0, then it will be that it will be I t 0, because at t is equal to t 0 you have to get the initial value, that is at t 0, that is I t 0. So, I infinity is there, and here instead of e to the power minus t by tau, here it will be e to the power minus t 0 by tau, right. So, if the current I 0 is 0, suppose if initial current is 0, then we can write I t is equal to 0 for t less than 0, and I t is equal to, because I 0 is equal to your what you call I 0 is equal to 0, then then it is V s upon R 1 minus e to the power minus t by tau if t greater than 0, and if we assume the initial current I 0 is equal to 0. This is equation 76, right. So, or we can write simply this thing, because it is t less than 0, t greater than 0, we can make it like this: I t is equal to V s upon R 1 minus e to the power minus t upon tau into u t. So, u t is 0 for t less than 0, so it will become 0, and for t greater than 0 u t is 1, it will become this thing. So, this two your what you call current thing can be combined, or can be written in one term, that is V s upon R 1 minus e to the power minus t upon tau into u t. This is equation 77, right. So, equation 77 actually gives the step response of the RL circuit with I 0 is equal to 0. The voltage across the inductor can be obtained from equation 77, right. So, that is V t is equal to L into d I t by d I upon d t. So, you take the derivative of this one, d I d t, right. If you do so, you will get V s upon R into L by tau into e to the power minus t upon tau, but L upon R is tau. So, tau will be cancelled. So, it will be V t is equal to V s e to the power minus t upon tau, but here u t is attached, right. That means, for t less than 0 u t is 0. So, it will be 0, right, and for t greater than 0 u t is 1, it will be V t will be equal to V s e to the power minus t by tau, right. So, that means, if you see this, so the step response of I t and this thing. So, when switch is closed for a long time for RL circuit, right. So, current is your I infinity as is V s by R. So, current is going to the steady state value V s upon R. Generally, after 5 tau, if tau is the time constant, it will achieve nearly V s upon R, and for t, when t is greater than equal to 5 tau, the V s is exponentially decaying. So, it will be your V t is decaying. So, it is gradually going to 0. So, at t greater than equal to 5 tau, it will become almost 0, right. So, this is the current plot, and this is the voltage plot for your what you call, that is your RL circuit with the step input, right. So, this is the step response of RL circuit with I 0 is equal to 0, no initial inductor current, right. A current response, and second is the voltage response. So, thank you very much, we will be back again.